Hi everyone, my name's Callum. I'm doing a PhD here at Manchester where I'm researching nuclear fuel cladding. And I'd like to speak to you today about how our research can help to develop cleaner, safer nuclear energy, much safer than the nuclear plant that Homer works at in Springfield at any rate. So, we want to continually improve our nuclear reactors so that they're safer, produce less nuclear waste, have longer lifespans, and are more cost efficient. One of the main ways that we can do this is by developing the nuclear fuel cladding. Now, for those of you who aren't familiar with nuclear reactors, this is the nuclear fuel cladding in a pressurized water reactor. It encapsulates the nuclear fuel and keeps it separated from the water moderator. And there's a lot of it in our reactors as well. The surface area of the cladding could cover 3/4 of a football pitch for one reactor. So it's really critical that we get this material right when we're developing it and putting it to use. In pressurized water nuclear reactors, the nuclear fuel undergoes fission, where it releases neutrons. These neutrons pass through the cladding and the water moderator before interacting with more nuclear fuel, although some are absorbed by the cladding. In passing through the water, some of the neutrons' kinetic energy is absorbed by the water, and this heats the water up. This hot water can be used to generate steam, which is how we generate our electricity. We therefore want as many neutrons as possible to pass through the cladding without being absorbed, so that the nuclear chain reaction can continue and the electricity generation can be at maximum efficiency. So when we're choosing our cladding material, first and foremost, we want to have a material that is transparent to neutrons released in the fission reaction. We also want our materials to be structurally strong and corrosion resistant. And the best all-round combination of these properties leads us to choosing zirconium alloys for our cladding material. Still, some neutrons that are released during the fission reaction will interact with our cladding. This video shows what happens when a neutron collides with an atom in our material, causing that atom to knock into other atoms, which generates a collision cascade. It's these events that damages our cladding, shortening its lifespan. These are some of the results of the damage mechanisms in our zirconium alloy cladding. Enhanced corrosion, leading to hydride and oxide formation, loss of coolant accidents, leading to ballooning, embrittlement, leading to fracture, and growth, leading to different fuel assemblies interacting with each other. To ensure a safe environment, before the damage ever gets to this point, we replace our fuel assemblies in a working nuclear reactor. Unfortunately, when we do this, we have to throw away the whole of the fuel assembly alongside it, including all of the unused fuel, so it all goes to waste. We currently have to throw away the fuel assemblies with 40% of the uranium still left, which is why a key challenge in improving our nuclear reactors is improving the longevity of our cladding, so that we can use up more fuel before having to replace it. We can improve the cladding by changing its alloying chemistry, improving the processing route during manufacture, or even by looking at coatings to the cladding. Over the years, this has been very successful in improving energy generation. To date, our advancements in cladding technology has led us to being able to double the amount of uranium that is used in the fuel assembly and increase energy generation equivalent to building 27 new nuclear reactor power stations in the US alone. That was a very brief overview of why it is important to develop nuclear cladding. This page just shows how every researcher in our team in Manchester is working on something unique to understand more about zirconium alloys and develop them further, so that we can continue to improve our nuclear reactors. Thank you very much for listening.